everyone, welcome back. It's me, the part-time economist, and in today's video, I'm going to show you how to conduct a one-way analysis of variance, also known as an ANOVA with Jamovi. Now, as part of this video, we're also going to talk about what an ANOVA is, why we would want to use it. Also, we're going to talk about the assumptions, the requirements to ensure that our ANOVA is valid, and then we will also talk about what to do if those assumptions are violated. So with that being said, let's go ahead, let's jump right in. Let's start with the big question right up front. Why would we want to use an ANOVA? We use an ANOVA when we are comparing two or more groups. So if you remember a previous video about the t-test, we said that the t-test allows us to compare two groups, right? So maybe it's before, maybe it's after, maybe it is class 1 versus class 2, right? But in the real world, we are often comparing more than two things, right? So maybe I have an 8 a.m. class that I teach, I have a 12 p.m. a lunchtime class that I teach, and then I have a 3 p.m. afternoon class that I'm teaching. And I want to say, of these three classes, right, is there a statistically significant difference in the average test score, right? I can't do that with a normal t-test, so that's why I use ANOVA. Now, as you'll notice here, I have the scores of all of the students listed on the left-hand side, and this is very important because these scores are numeric. When we are doing an ANOVA, our dependent variable needs to be continuous, right? So it needs to be interval or ratio data. Here, we're working with numbers that range from 0 to 100, so we're good. But we couldn't do something like colors, for example. Now, you'll also notice that I have this grouping variable. So I've got A, B, and C to indicate what class the student belongs to. So with that being said, we're going to go to analysis. We're going to go to ANOVA, one-way ANOVA. Now what we're going to do, we are going to move the score to the dependent variable. We're going to move the class to the grouping variable. And what we're going to do, we are going to assume equal variances. We'll talk about that in a minute. And what this is going to do is it's going to calculate all of the information that we need. So as you can see here, our F statistic is 40.4. Our p-value is less than 0.001. So what does this tell us? Well, this essentially tells us out of these three different groups, there is a statistically significant difference, right? At least one group is different from the others. Now, that's kind of only a partial success, right? Because it's one thing to know that a group is different, but we have no idea which group it is, right? Is it group A? Is it group B? Is it group C? So what we need to do now is something known as post hoc testing. Now, what the post hoc testing does is it goes through and it compares each group to every other group. So just for starters, we're going to use Tukey, and we'll talk about why we're doing that in a minute. But we're using Tukey, and essentially it's going to go through and it's going to say, look, is group A different than group B? It's going to give us the p-value, and we see that yes, it is. It's going to say, is group A different than group C? Again, yes, it is. And then finally, is group B different than group C? Obviously, the answer here is no. So the ANOVA really is composed of two parts, right? The first part is this overall, is there a difference, right? If we would have done that original ANOVA and there was no difference, we can stop there. We can say, hey, all of these three classes, they're the same, right? There's no significant difference. But if we do have a difference, that's when we need to do the post hoc testing. So when I was doing this, I kind of just breezed through a few things that are actually really important. The first thing that I did was I clicked to assume equal variance. Now, when we're doing an ANOVA, the default assumption is that the variances are equal, right? That's an assumption of the test, but what we want to do, we actually want to verify that that is the case, and we do that by going to this assumption checks. We click on homogeneity of variance, and it's actually going to tell us that based on this data set, that assumption is violated. So this can lead to a problem, right? If we are saying calculate these statistics based on the assumption of equal variances and we don't actually have equal variances, we're not really doing what we're supposed to do, right? So if that's the case, if that assumption is violated, we can check this that says don't assume equal variances. Now, in this example, it's going to give us the same result. P-value is still going to be less than 0.001, so not a huge problem, but it is something you need to be aware of. Now, also, that comes into play on the post hoc testing. If we said that these variances are not equal, we can't use Tukey, right? Because Tukey is assuming equal variances. So we've got to come back and use the James-Howell test instead. Now, as far as this analysis, again, it gives us the exact same results, right? The p-values, the rejection, all of that is pretty similar, but there could be a data set where it is different, right? Where you don't get the same results. So it is important to verify that assumption. Now, the other key assumption when it comes to the ANOVA is normality. Now, normality is an assumption of pretty much all tests, right? So we always want to be testing for that. But what you'll notice here is that we reject that assumption as well. Now, again, this is a problem. If we are doing a test that assumes normality and we don't have normality, again, that can set us up for problems. So what we want to do instead is we still want to do this comparison, but we can't really do ANOVA. So what do? We come up here to ANOVA. We go to non-parametric alternatives. Now, the non-parametric alternative to the one-way ANOVA is Kruskal Wallis. So again, we're going to go with score as dependent, class as the grouping variable. And again, it's going to tell us our p-value less than 0.001. So again, we reject the null hypothesis. We conclude that at least one group is different than the others. Now, again, we run into a similar problem where we don't know which group is different. So what we can do, we can click on either of these post hoc tests. Let's just go with this one. And what it's going to do, again, it's going to do that pairwise comparison, right? So group A versus group B, there's a difference. Group A versus group C, there's a difference. And then group B versus group C, there is no difference, right? So if I was looking at this data, I would say, look, there is clearly a difference. Group A is really standing out, right? Group B and C are about the same. So that makes intuitive sense, right? I know I'm using fabricated data here, but I set it up this way. And there's a logical explanation for this, right? My 8 a.m. class, the students are probably absolutely tired. They are worn out, right? Like it's first thing in the morning. So it makes sense that they would have a different average score than B and C, right? The lunchtime group, the afternoon group, right? Like the lunch group, they're excited. They've woken up. They've got lunch after this. The afternoon group, again, they've got food in their belly. They're ready to learn, right? So, that's an overview of how you do the one-way ANOVA and the Kruskal Wallis in Jamovi. I hope you found the video useful. Thanks so much for watching, and I will see you next time.